This talk is going to be about aerosol sampling. One of the first things we need to do if we're going to sample for an aerosol is know what an aerosol is. And an aerosol is defined as an assemblage of solid or liquid particles dispersed in a gaseous medium. There's a lot of different types of aerosols. There's dust, which are dry particle aerosols produced by mechanical processes such as breaking, grinding, and pulverizing. Essentially, if you're doing any sawing or sanding or blowing something up, the dry particulate matter that is suspended in the air is considered a dust. Fumes are a very fine solid aerosol particle produced from vaporized solids. This is, for example, if you are welding and some of the vaporized solids come off of a weld, when they get to cooler air and condense, they'll form solid aerosol particles that are defined as fumes. Mists are spherical droplet aerosols produced by mechanical processes such as splashing, bubbling, or spraying. A fog is an aerosol droplet produced by condensation from the vapor phase. And smokes are complex mixtures of solid and liquid aerosol particles, gases, and vapors resulting from incomplete combustion of carbonaceous materials. The last type of aerosols are fibers, and these are elongated particles having an aspect ratio, which is a length to width ratio greater than 3:1. So objects like a javelin or a pencil that are longer than they are wider by at least a 3:1 margin are classified as a fiber. There are different types of aerosols that you may encounter in occupational environments. The first is polydisperse, and that means that you have a wide range of particle sizes, and this is typical of workplace environments. If someone is sanding sheetrock, for example, you're going to find particulate matter that's suspended in air that have a wide range of different particle sizes. Monodispersed aerosols contain only particles of a single size, and this is typically for a research application. If a researcher is interested to know how a 4-micron particle may behave, or if they need a specific size of aerosols for a specific application. For example, in an inhaler for drug delivery, they may need particles only of respirable size, so they may have an aerosol cloud that contains particles of a single size. So there are some different types of aerosols that can be encountered in different environments. Aerosol morphology is a description of its shape and appearance. Aerosols can be spherical. Fumes, for example, are generally spherical when metal fumes are formed from condensation. Several of the bioaerosols, different types of spores, for example, are spherical. But most aerosols are isometric, and that means that their dimension is independent of orientation. Dust from pulverizing, grinding, processes, etc., are going to lead to isometric aerosol morphology, as well crystalline particles are isometric. You can think of these as like snowflakes or meteorites or something like that, where they come in all different sizes and shapes, and these are going to be typical from occupational environments. So most of the aerosol clouds that you'll encounter from workplaces are going to be polydispersed, meaning that there's all kinds of sizes, and isometric, meaning all kinds of different types of orientations. These are some pictures of different types of aerosols. This is a silica particle, and as you can see, this is considered to be an isometric orientation, meaning that its length is independent of its orientation, and you can see a lot of projections on it that are going to be unique to this particular particle. Another silica particle is going to look similar but not exact to this. This is a concrete particle, again an isometric orientation, and this is an electron scanning image of what a concrete particle looks like. This is the asbestos fiber. This happens to be a chrysotile asbestos fiber, but as in most fiber materials, it's going to be at least 3 times longer than it is wide. This is a dust mite pellet, and as is the case for many bioaerosols, it's spherical in nature. And this is a chart from your reading assignment that just lists a lot of different types of aerosols and how they fit within a size scan. Now, when we sample for aerosols, the reason that we're sampling for aerosols is because certain types of aerosols can deposit in the lungs and have some pretty profound biological effects. In fact, in the industrial hygiene world, if you look at all the different exposures that have caused the loss of human life, aerosol inhalation has killed more people than anything else. And so it can be very dangerous to inhale different types of aerosols. And so when we sample for aerosols, what we're interested in doing is trying to determine what concentration of aerosols that are present that have the ability to hurt the lungs. So in order to know air sampling for aerosols and why we do it, you need to know a little bit about how the lungs actually work and why certain aerosols of certain sizes will deposit in one area of the lungs and not in another. Now, where do aerosols deposit in the lungs? That's what this is meant by aerosol deposition mechanics. The dose, or how much of the aerosol gets into the lungs, is primarily influenced by the aerosol's physical properties. Now, there are a lot of physical properties that an aerosol has, but the most important is particle size. The size of the aerosol is largely going to influence where it ends up going into the lungs. The shape can play an influence as well. The density of the aerosol can play an influence as well, and its hygroscopicity, which is the ability to absorb water, can play an influence as well. And the last is important because if an aerosol has the ability to absorb water, its size is going to change as it traverses the wet area of the respiratory tract. Now, when aerosols are deposited in the lungs, they do it by a known process, and I want to talk about a couple of them: sedimentation, inertial disposition, diffusion, and interception. Sedimentation results from aerosol particles settling out by gravitational forces. And in parts of the respiratory tree, the heavier particles will settle out, the lighter particles will remain suspended in air. Sedimentation is going to be dependent upon air velocity. And so areas of the lung where the air velocity is highest, i.e. nearest the trachea, are probably not going to have as much sedimentation occur as in areas of the lungs where airflow is slowest, i.e. the air sacs of the lung. So where it's windy, sedimentation doesn't occur that often. Where the air is still, sedimentation is going to occur pretty predominantly. Inertia, or inertial disposition, occurs when there's a fork in the road, and there are lots of forks within the respiratory system. They're called bifurcations. And the heavier particles will be carried by inertial forces, and impact the bifurcations and remain there. Whereas the smaller particles are going to remain suspended in air and essentially go with the airstream. And the inertial disposition is a major factor in the areas of the respiratory tract where there's a lot of branching, and this will occur in the tracheobronchial region of the lung, where you'll see a lot of branches, and the smaller particles will be able to traverse the branches, go with the flow, so to say, and the larger particles will smash into the bifurcations and be stopped there. Now, diffusion down at the bottom is basically when very small particles will dissolve in the lining of the respiratory tract. The respiratory tract is kind of like sticky flypaper. It's moist, and if you have a real small particle that can adhere to the side, it can dissolve in the respiratory tree itself, and that process is referred to as diffusion. Oh, one more thing. The last thing on the aerosol disposition mechanics, the last is interception. This is specific for fibers, and you can think of it as sort of throwing a javelin and having it stick in the ground. It will adhere by the process of interception. So it's sort of a long, skinny object poking into the side of the respiratory tract and remaining lodged there. And when it's lodged there, it's lodged by the process of interception. Now, particles will behave differently in different areas of the respiratory tract. There are three areas of the respiratory tract that you need to be familiar with. The first is the nasopharyngeal region, the second is the tracheobronchial region, and the third is the pulmonary region. These are represented here. The nasopharyngeal region is the upper portion of the respiratory tract where your nose and throat are. The tracheobronchial region are where the trachea branches off into the bronchi, and you have many of these bifurcations that I mentioned earlier. And the pulmonary region is the lower region of the respiratory tract where the air sacs are. This is the business end. The pulmonary region is where you have oxygen that is capable of crossing the very thin membrane of the pulmonary region into the bloodstream and collecting the carbon dioxide that's released from the bloodstream back into the air sacs where you'll exhale it. The rest of the region, the nasopharyngeal and the tracheobronchial, are the pipes, but the business in is the pulmonary region. Now over here on the other side, I have three terms: inhalable, thoracic, and respirable. And what these refer to as, we'll talk about a little bit later when we talk about particle size, is that smallest particles can make it to the pulmonary region, and those particles can do the most harm. And if we want to sample for the fraction of a particulate cloud that we know is respirable, i.e. can make it to the pulmonary region, we'll have a cutoff point for our air sampling, and that cutoff will be directed at just collecting the particles that can make it to the pulmonary region of the lungs. If we have a thoracic fraction, we're dealing with particle sizes that are able to make it to the tracheobronchial region and the pulmonary region. And if we're taking an inhalable sample, or the inhalable fraction, these are any particle sizes that can get inside of the respiratory tract. This is a slide that demonstrates how aerosols can traverse the respiratory tract. You can see large particles will come down and impact in the bifurcations. Smaller particles will go with the airflow and may settle out by gravitational forces, by sedimentation. But the very smallest particles down here are going to be able to make it to the air sacs of the lung. And again, they can do tremendous bodily harm by being able to get into the air sacs. Now, what kind of factors will influence the disposition of the aerosols? First of all is the nature of the aerosol itself, and we talked about that a little bit earlier. And the main factor there is the particle size of the aerosol, the exposure conditions, whether it's windy outside and the concentration in the air and things like that, and the characteristics of the individual, how their breathing patterns are, if they're a nose breather versus a mouth breather. Nose breathers will tend to have the nasal hairs in their nose intercept some aerosol particles before they get into other regions of the respiratory tract, where a mouth breather, they can have greater access to the tracheobronchial region. So there are different factors that will influence the deposition. Then there are factors on the respiratory tract itself. There's the lining of the tract, which is like a sticky flypaper. There's branching that occurs. In the tracheobronchial region, there are thousands and thousands of branches that are needed to traverse before getting into the air sacs. And then there's air velocity. And air velocity will be very high in the nasopharyngeal region, but it will be progressively slower as resistance will occur with each branch that will progressively slow the air velocity down to when you get to the terminal regions of the respiratory tract, the pulmonary region. The air velocity is very slow in that area. Now, if we get an aerosol inside of our lung, how do we get it out? The clearance of aerosols is going to vary dependent upon what region of the respiratory tract the aerosol has deposited in. If an aerosol deposits in the nasopharyngeal region, it can be cleared by processes such as coughing and sneezing. If an aerosol will make it to the tracheobronchial region, we have what's called a mucociliary escalator. And this is a process by which mucus is pushed upwards by columnar epithelial cells that have cilia at the end of them that basically beat in rhythm to push mucus upward. We swallow about a quart of mucus a day from this clearance mechanism, and what it's doing is it's a smooth muscle mechanism that will help clear particulate matter that may have deposited in the tracheobronchial region, and you'll eventually clear it out by swallowing it. If you are exposed to an irritant, such as cigarette smoking or other types of irritants, you can damage this process. And what will happen with people, especially people that have smoked 2 to 3 packs of cigarettes a day for decades, they have burned the cilia off of these specialized cells. But the mucus is still there and still needs to be cleared, and so you'll see that they have a deep hacking cough, a smoker's cough. And the purpose of this is to try to clear the mucus out that ordinarily would be done by the mucociliary escalator. The last region of the lungs, the pulmonary region, if particulates make it to that point, they're cleared out by either macrophages or by the lymphatic system. Now the problem with this is that it's a very slow system, and the macrophages are very fragile, and they have digestive enzymes inside of them. So if a macrophage tries to clear out an isometric aerosol particle, like a silica particle, that has sharp projections on the sides, it can damage the macrophage, and the macrophage can then leak its digestive enzymes out into the lining of the lung. It will put down some scar tissue when it repairs, and over years and years of this occurring, the lungs go from being a balloon that can expand and contract readily to a massive scar tissue that can't expand and contract at all. It's restricted in its ability to move, and that leads to restrictive diseases. And these restrictive lung diseases, like silicosis, for example, are debilitating and fatal because they impair the lung's ability to expand and contract. Now, if an aerosol gets into these various regions of the lung, the nasopharyngeal region, for example, you can usually clear it in a couple of days by coughing and sneezing. If it gets into the tracheobronchial region, the mucociliary escalator will clear it up, you'll swallow it, and so the total residence time in your body might be a week. And if a particle gets into the pulmonary region, in healthy adults, by using macrophages or the lymphatic system to clear it, it may take years for a particle to be cleared. And in people that have had some kind of impaired problems with the lung, they may never get rid of it. And in fact, there are many cases on autopsy of people that have died from pneumoconiosis, diseases of the lungs, where on autopsy they section the lungs and sand basically pours out of them because there's been so much particulate matter that's accumulated, and your body really is very limited in how it can get rid of it. So it's real important to sample aerosols and to protect against aerosols that can make it to the pulmonary region of the lung, because we can't get rid of them very readily. Now, I don't like to use numbers because they vary depending upon your source, but as a general rule, larger particles are going to deposit in the nasopharyngeal region, the mid-sized particles in the tracheobronchial region, and only the smallest particles can make it to the pulmonary region. Usually anything greater than 10 microns will deposit in the nasopharyngeal region. Particles that are in the 5 to 10 micron range will be in the tracheobronchial region, and particles that are under 5 microns can make it to the pulmonary region. But again, these numbers aren't set in stone, and there is some variation. But most of our respirable samples, that is, sampling that's designed to try to count the number of particulates, or the amount of particulates that make it to the pulmonary region, the respirable particles, usually those are designed to be 5 microns or less. So we consider the 5 micron or less to be the cutoff for particles being able to make it into the pulmonary region of the lung. And those particles of 5 microns and smaller are extremely dangerous because of our limited ability to clear them out of our lungs. Now, aerosol sampling in the workplace is designed to prevent pulmonary damage. I have a link here from some specific procedures that are available from the OSHA website on how to do dust sampling. You can go there, that you can look at later. And the different ways that aerosols are collected are going to be based upon the processes by which they settle that we already talked about. For example, you can have collection mechanisms that are based upon sedimentation, by seeing how long it takes for an aerosol to settle out by gravitational forces. You can collect on B here by impaction, where you have a series of one plate or more plates, where particles of a certain size will collect on the bottom of the plate and smaller particles will go with the airflow. Or you can collect by particles adhering by the process of interception, which could occur with a fiber. And this is a graph of collection efficiency as a fraction of total aerosol samplers. And what I wanted to point out is that this has both an inhalable, a thoracic, and a respirable collection, so you can differentiate between different particle sizes that can be collected on these three types of cutoff points. Now, aerosol sampling can be based upon different types of techniques. You can use a size selective sampling. And with this, you can use filtration-based techniques, i.e. gravimetric analysis, where you can have different types of filters, and you will collect the aerosols on the filter. You can weigh your filter before you begin collecting the aerosol and after you've begun collecting the aerosol, and you can determine then how much aerosol is present in the environment based upon the difference in the weight of the filter and the known quantity of air that's been pulled through the filter. This is some filter cassettes. These are styrene acrylonitrile cassettes used for particulate sampling. In this case, asbestos sampling. And you'll pull the asbestos-laden air through these filters. You can weigh them both before and after and get an idea on how this is how much has been deposited on the samples. I guess A is the styrene acrylonitrile. B is the asbestos sampling, but these are, again, examples of different types of collection media that can be used to collect aerosols. This is an inhalable dust sampler, and this is one where you would collect inhalable particles. These are particles of any size that are capable of entering the lungs. Now, aerosol sampling can also be based upon sedimentation-based techniques, and for this, the most common is centrifugation. This is an example of a idealized horizontal elutriator, which collects aerosols based upon their settling velocity. And this is a cyclone separator. This is probably the most common type of respirable sampling device. And what it relies on is centrifugation. What will be happening is that you'll be pulling in dirty air here, where this arrow says, this arrow on the left. It will enter this cyclone, and it will spin around much like the vortex of a tornado. And what will happen is that the heavier particles will crash against the sides and be collected down below, and the partially cleaned air, which has the finest particles, will go up above to some kind of a filter, where you can collect those filters and therefore determine how much is present. So the larger particles that you're not interested in can fall down below, and particles of a certain size, and most respirable samples have cutoffs of 5 microns, so particles that are 5 microns and below can be collected in this partially cleaned air stream that's above. This is an example of how one's put together a little bit more. Again, the air will come into the cyclone, spin around. The heavier particles that you're not interested in are going to fall below in this grid pot, whereas the lighter particles are going to go ahead up to the top, where the airflow is going towards the top of this picture, be collected on this filter, and you can measure them later. So generally, particles that are 5 microns or less can be collected on this filter and measured. And you would measure them by weighing the filter before you begin collection, weighing it after you've collected it. The difference between the filter rate with and without the dirty air is going to be the amount of particulates that you've collected in the 1 to 5 micron range. And so you can base your data on milligrams per cubic meter because you know how much airflow has gone through the cyclone sampler. Aerosols can also be sampled by impaction-based techniques. These can be single-stage impactors, cascade impactors, and liquid impingers. And this is an example of an impaction. You can have a one-stage cutoff impactor. You could cut this off at 10 microns, so any particles that are larger than 10 microns will crash on this plate on the bottom of A on the left-hand side of your screen, whereas the larger particles will go with the airflow, or excuse me, the smaller particles will go with the airflow, and you can collect on your filters. So you can use this to have a cutoff of 10 microns that will crash, and 10 microns and below that will stay with the airstream. In the middle is a cascade impactor where you can have a series of plates, and you can collect particles on different sizes on this plates. And the way that it works is that the heaviest particles or largest particles will crash on the first plate. The lighter particles will go around on the edges and continue with the airflow. The next heaviest particles are going to crash, or largest particles will crash on the middle plate. The smaller particles will go with the airflow around to the sides, and smaller particles yet will collect on the third plate. And you can have many stages on this. This happens to be a 3-stage cascade impactor. I think Dr. Attia has a 5-stage Anderson cascade impactor in the industrial hygiene laboratory. And why this is useful is that you can have a polydispersed cloud of aerosols, and using this technique you can determine how many of the aerosols that are in that cloud are 10 microns or greater, how many are 5 microns or greater, how many are 1 micron, etc., depending upon what sizes the cascade impactor is designed to collect. And this is a liquid impinger. Liquid impingers are some of the earliest methods of sampling for aerosols, where you bring in a stream of dirty air. The air will stay behind in the impinger. The dirt will stay behind in the impinger, and the clean air will go out the side. What earlier industrial hygienists used to do is that they would collect particulate matter in a known volume of water. Then they would agitate it, stir it up as much as they could, take an eyedropper with perhaps 1 mil of liquid, put it on a grid on a microscopic plate, and count the particles. This is a tedious method of counting aerosol concentrations, but it was an efficient one that was used in industrial hygiene for a number of years before some of the better techniques have come along. But it works on the process that if you have dusty air going through water, the dust will stay behind and the clean air will go out the other side. Then there are other techniques, such as optical techniques for optical microscopy and electron microscopy. And some of the earlier slides that I showed you on silica particles and dust mites were slides where that were taken by either one of these two techniques to look at aerosols and determine what type of aerosol was present. So that concludes my discussion of aerosol sampling.